My bananas are telling me that it's time to answer your burning questions. At least, I think that's what they want. A natural place to start is with the most common question we've received. Why have an odd number of bananas in the Even Bananas logo? Lots of reasons. Aesthetically speaking, 3 is the magical, beautiful number. We weren't thinking about the word even in that sense, and frankly, because it makes me laugh. But more importantly, it symbolises the 3 flavours of neutrino: electron, muon, and tau. Now that the hardest question is out of the way, let's get on to more of your science questions today on this episode of Even Bananas. Our first question is one that really gets to the heart of the scientific questions we're trying to answer at Fermilab. How many layers of custard does it take to block a neutrino? First off, let's assume we're talking about a neutrino from one of our accelerators at Fermilab. It's an important distinction because a neutrino's energy changes how likely it is to interact with other particles, and that includes the ones in desserts. I've got to be honest with you, I thought this would be an easy question to start with, a nice back-of-the-envelope calculation that we can all do together. All we have to do is work out how likely a neutrino is to interact with custard, stick that in the equations, and then we can spend the rest of our time thinking up great custard-based jokes. What do you call custard when it goes bad? Off-pudding. What is custard's favourite Olympic event? The 100-metre hurdles. Custard, I'm your biggest flan. It turns out that first part is a bit tricky. Shockingly, no one has ever measured the neutrino-custard interaction probability, so we're going to have to make a few important assumptions. Custard has a pretty complicated chemical composition, but it contains a lot of water and a lot of molecules called hydrocarbons. That means there are plenty of carbon and oxygen atoms for our neutrinos to interact with. The probability for an accelerated neutrino to interact with those atoms is about this. Assuming that our custard has a slightly higher density than water, we can expect about 35 sextillion atoms per cubic centimetre. Next, we can calculate something called the mean free path, which is the average distance you would expect the neutrino to travel in our custard before it gets stopped, by doing 1 over the atom density multiplied by that interaction probability. That gives about 10 times the distance between the Earth and the Sun. And of course, the final piece of the puzzle, how thick is a layer of custard? Well, first of all, it turns out there are multiple different definitions of custard. I am British, so I think custard is this. After careful dessert-based scientific research, I have determined the answer to how thick is a layer of custard is about 0.5 centimetre. Any more feels gratuitous, any less seems like a waste of time. So, the answer to how many layers of custard does it take to stop a neutrino is at least 300 trillion. We're going to need a lot more eggs. We've had quite a few viewers ask this question. Were neutrinos produced in the early universe, and can we detect them? I am so happy you asked. The answer to this question is a very cool phenomenon that we haven't talked about at all before. You might have heard of something called the cosmic microwave background. That's the electromagnetic radiation that was left over from the creation of the universe. From a particle physics perspective, it's made up of photons, particles of light. But here's something you might not have heard of, the cosmic neutrino background. As you might be able to tell from the name, it's similar, but with neutrinos. The really cool thing, though, is when these neutrinos come from. The cosmic microwave background is photons from 380,000 years after the Big Bang. But the cosmic neutrino background comes from when the universe was just 1 second old. Take that, photons! Now, obviously, if we could measure these neutrinos, that would be amazing. We could learn a whole lot about how the universe evolved if we could see all the way back to a second after the Big Bang. Unfortunately, neutrinos in the cosmic neutrino background are very low energy. And as you know, low energy neutrinos interact even less than medium or high energy neutrinos. When they do, they're harder to spot. In fact, no one has actually figured out how to measure these neutrinos yet, but someday I'm sure someone will come up with a great idea and it will be groundbreaking when they do. It might even be you. Our next question is another really important one. How do we stop neutrinos coming into our experiment from outside? The short answer is we don't. It's basically impossible. We're actually more worried about keeping out other kinds of particles that are more likely to interact and give us false signals, like muons from the atmosphere. We protect against those by adding some material that absorbs them, or by putting our experiments underground. This leads to another common question. How do we know we're seeing neutrinos from our accelerator and not from some other random source? First, we can sort of tell the direction of the neutrinos coming into our detectors, because conservation of momentum tells us that if a neutrino is going forwards and hits a stationary atom, then most of the particles produced in that interaction will go basically forwards too. They don't all go exactly forwards though. It's kind of like when you brake in pool. The general direction of all the pool balls is forward, but some of them go more to the side than others, some of them bounce off each other, and some of them can even end up going backwards. But still, by looking at the direction of the particles we see in our detectors, we can work out roughly where the neutrino came from, and if it's likely to have come from our accelerators or not. The other trick we have is to look at the difference in how many neutrinos we see when our accelerator is on versus when it's off. If we see more neutrinos when our accelerator is running, then we can be pretty confident that we're seeing neutrinos from the accelerator, even if we can't point at which exact neutrinos came from the accelerator compared to somewhere else. Next question. A lot of you keep asking where Don is. Turns out he's here in this video. Hi Don! And he's going to answer a very popular question. Can neutrinos pass through a neutron star? Don?
Hi, Kirsty. That's a great but very difficult question to answer. Neutron stars have a mass just a little more than that of the Sun, packed into a sphere with a diameter of 20 kilometers. While neutron stars do have a crust and a core kind of like the Earth, you can sort of think of them as a single atomic nucleus the size of a medium city that contains only neutrons, and they're all packed tightly together. So, can neutrinos pass through neutron stars? It depends on a ton of factors, including the star's temperature, pressure, age, thickness, and what kind of matter exists in the core. Is it just neutrons, or is it quark matter, where the neutrons are broken? We don't know the answer to that, but a recent study strongly disfavors the quark matter idea. Making a few assumptions and knowing that our understanding of neutron stars is incomplete, the answer largely comes down to the neutrino's energy. Neutrinos from a particle accelerator with moderately high energy would not make it far into a neutron star. Going to lower energies, say 100 times lower, neutrinos could travel maybe 1 to 10 kilometers into a neutron star before being stopped. Getting down to the energy of solar neutrinos, say 10 times lower still, things get trickier. In principle, these neutrinos should pass through a neutron star. In fact, because of quantum effects, a neutron star should be transparent to these low-energy neutrinos. Doing this calculation right is hard. Back to you, Kirsty.
Okay, now it's time for a lightning round. I have not been prepared for these yes or no questions, so anything goes. Fire away, team. Can neutrinos be destroyed? Yes. Some of those types of neutrino interactions we've talked about, where a neutrino comes in and a lepton of the same flavor goes out, no neutrino left at the end, neutrino gets destroyed. Provided we could detect neutrino emissions from humans, as mentioned in our video, would it be possible to, so to speak, scan for life forms? I don't think so. The problem is, I don't know how your scanner is going to be able to tell the difference between a human and a human-sized pile of bananas. Are neutrinos made up of even smaller particles? No. We think neutrinos are fundamental particles, which means we think they are the smallest thing, and they're not made up of anything else. If, let's say, a neutrino does interact with my body, will I feel anything, a shock or a burn or anything? No. In fact, I know this from experience. I have stood in the neutrino beam at Fermilab, didn't feel a thing. Is Kirsty Daffi from Bristol or round about there? No, not at all. I'm actually from the northeast of England near Middlesbrough, and then I spent nearly 10 years in Oxford and then 4 years in America, so I don't know where my accent is from these days. The neutrinos depicted kind of looked a whole lot like vanilla, chocolate and strawberry to me. Was that intentional? Absolutely. All things, and even bananas where possible, are modelled on food. Are neutrinos their own antiparticles? I don't know, but I wish I did. It's one of the really big questions about neutrinos. Unlike other particles, they could be their own antiparticles, but we just don't know. A lot of people are doing experiments right now to try and work it out. That was the lightning round. I hope I passed. But finally, thank you for all of your suggestions on topics for future episodes.